All right, so here's the deal. I'm just going to sort of eventually throw open the floor, and I'll try to determine an order for answering the questions. And then, you know, you don't get to ask two in a row unless you really, really beg because you have to go because you have another exam or something like that. So I try to be fair in that sense. But anything from previous finals or homeworks or anything like that is fair game. So any general questions before I begin? General question.
What's the format of the test?
What's the format of the test? They probably did it in LaTeX. Oh, you don't mean what program? You mean, okay, look, it's just a 3-hour exam. I mean, I don't know. I haven't seen it, so I can't really say. But if you look at previous exams, you'll see they tend to have between 7 and 12 questions. There's between a quarter and a half has been on pre-midterm stuff exclusively. Of course, there can be some questions on this integration stuff that have something, like Part A could be something to do with pre-midterm stuff as well, so it's sort of hard to distinguish. But, you know, the recent ones are probably a better guide for what this one is going to look like than the older ones. But all those questions, every question that I've seen is fair game. I don't think there's been any change to the syllabus substantially in the last 15 years. So all of those papers are good. Do you need a calculator? I believe you're not allowed to use a calculator. That's true, right? No calculators allowed? Okay. So you need no calculator. You need the absence of a calculator. Any other general sort of questions? Yes, up the back. You know, I have some of the copies, not the older, very old finals, but I think I have all of the ones that say that were under the practice exam. So we should be able to sort those out if you want to refer to them by that. On the other hand, in my preparations for this, for yesterday and the day before, I kind of sort of got them all messed up. So I don't necessarily remember which one is which, but I should be able to mostly say 80% of those problems actually just find them in my stash here. All right, so yes, you can refer to the problems like that. All right, so are there any other general questions? Okay, so who wants to ask me something? Okay, one hand has gone up, so you get to go first, and then you can be second, and then we'll see how we go. Number 9. Okay. So this is from May 2005. Remind me to give this back to you. I have one of my own over here. May 2005, question 9 is the thing. So once again, I'm just going to use the top half of this board. I see that you've all clustered on this side of the room, which is pretty wise. Now I might even use the right-hand board a little more, and the lectern won't get in the way too much. Okay, so for those of you who don't have it, S is the part of the surface z equals x squared plus y squared that lies below the plane z equals 4x minus 3. R is the shadow on the xy plane. And you're supposed to set up but not evaluate an integral for computing the surface area of S in rectangular coordinates. That's the first part, and the second part's going to be in polar coordinates. So I'll give this back to you now. So the first part is, so we want to set up an integral for evaluating the surface area as this form. We need a double integral of something dy dx. That's given in the question. By the way, it could be dx dy or dy dx, but they specifically said dy dx, so we better follow that. So the aim is to fill this in and fill that in, and that's basically what the problem is. So let's draw a little picture of the thing. Z equals x squared plus y squared is what? It's a paraboloid. The way we can tell is if it was z squared equals x squared plus y squared, it would be one of these other things like a hyperboloid or a sphere. In this case, it's a hyperboloid. But the paraboloid comes when one of them is linear and it doesn't have a quadratic. And in fact, if you just draw z equals x squared or z equals y squared, you just get the regular parabola, and that's just revolves. So this is all pre-midterm stuff. We know it's a paraboloid. z equals 4x plus 3 is a plane. It's a plane, and to find what it looks like, here's z, here's x. I'm just going to draw the line z equals 4x minus 3. So here, okay, in the zx plane, it would look like this. It would have intercept minus 3 and slope 4. So it'd sort of be like that. So now I've got to draw that, but sort of this has to be revolved and put over here. So that's z is minus 3 is down there. So the line is like that. And it's not a line, it's a plane because y doesn't come into it. So it's sort of all of this. So it's sort of hard to see, but this is going to shave off a little bit of this, this parabola here. Paraboloid. It's kind of hard to visualize what it is, but basically we've got this bowl and we're just slicing off a little bit. So you'll actually end up with something like this. Just a little cap, really, of the thing. It's this very small bit of surface. Okay? So that's the geometry of the thing. Now, the first thing I think we ought to do is work out what the shadow on the xy plane of this object looks like. Okay, so basically, how do you do that? Well, you more or less ignore z. Or if you like, you think of it this way. So we've got to first find r. You don't have to do it first. There's a bunch of different things to do in different orders. But basically, first I'm going to find r. So what I'm going to do, I've got to pick a point xy and find z, basically, is what it is. Well, we know what z is. Actually, z equals x squared plus y squared. No problem, it's given in the equation. We don't even have to solve for it. So we just have to work out which x's and y's are acceptable. And what do I mean by acceptable? I mean that I need something below z equals 4x minus 3. So if you look at what's below this on here, you need z to be less than or equal to 4x minus 3. That's the below part. So we need z less than or equal to 4x minus 3, i.e., we need x squared plus y squared less than or equal to 4x minus 3. I'm not going to go much further down here, but let me just say that in order to get this, I'm going to subtract 4x and I'm going to add 4 to complete the square. In other words, we've identified r just by factorizing. I guess I should, or factoring this, you will get x minus 2 all squared plus y squared is less than or equal to 4 minus 3 is 1. So R, the region, looks like this. If this was equals, it would be the circle center 2, 0 of radius 1. And because it's less than or equal, it's basically the interior. So your paraboloid, this is in the xy plane. If you think of z as coming out of the board, the paraboloid is like a bowl. And we just need the bit carved out by this. So it's going to sort of carve out this sort of surface that's just sitting above but is curved. This is flat, and it will be sort of like this, a circle that's distorted. So pick this off the page and pull this more. It'll curve around a little bit. That's what we're looking for. Okay, good to visualize, even though really all you need to do is find r. Okay, so that's the first thing. Now the second thing is we need to deal with sigma. Now, from what I said yesterday, you have to find an equation for the surface in the form f equals, well, let's do f equals x squared plus y squared minus z equals 0. So we had z equals x squared plus y squared. I just put the z on one side. It doesn't matter whether you put the minus minus plus here or plus plus minus. All right, so then we needed to compute grad f. So that's 2x, 2y minus 1. We're going to need the norm of grad f. So that's just 4x squared plus 4y squared plus 1. You square all those components. The minus 1 squared is 1. And we also need the k coordinate, or the k component, the z coordinate of this, which is just minus 1. And we need the absolute value of that. So it's 1. And so we have our standard formula, d sigma is equal to the length of grad f over the absolute value of the k coordinate, or the z coordinate of grad f, dx dy, or in this case dy dx. And so we just have already computed this as this quantity divided by 1 dy dx. And as I recall, this came up in a problem yesterday, a different problem that we looked at. Same d sigma. So we're ready to put everything together and then do both. Well, we're going to do this part first and then we'll look at the other part. So let's see, what's our question? We start off with 1 d sigma, that's the surface area. The question was set up the surface area of that thing, right? It didn't have a different function there? Okay, good. That's what I thought. Right, so according to the standard formula, this is equal to the integral over r. The 1 stays by itself, and then we have this mess here. D sigma becomes that, which is just root 4x squared plus 4y squared plus 1 dy dx. Okay, so that's, and of course you don't need the 1 here. I was just emphasizing that it's a surface area integral of just the integrand is 1. Okay, so that's sort of the answer to both parts in a way. The second part is, of course, to do it in polar, but they want to see an explicit representation in Cartesian coordinates, and this r is the problem. So in order to do it, we're going to have to set up the correct bounds. And now, by what I had said right at the beginning on Tuesday, you fix x and you see what y does. So in this diagram, I'm going to fix x. So that corresponds to a vertical line. And I got to see what y does. Well, if you solve this equation for y, you find that y squared, I'll just solve the equation of the equality, is 1 minus x minus 2 all squared. So y is plus or minus the square root of this. And of course, the minus is the bottom half, and the plus is the top half. So y in is the negative, and y out is the positive. So that means, when we put that into the shadow, the integral in rectangular coordinates, same integrand, and for fixed x, we've decided y goes from minus the square root of 1 minus x minus 2 all squared to plus the square root of 1 minus x minus 2 all squared. Maybe it would be a little bit nicer to shove this aside so it wasn't in the way. When you write it up, I wish I had a word processor. Space, 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 space. Okay, then we just have to fill in this. Where's the first x? Well, if you look up at the picture over here, you see the first x that's relevant is 1, and the last one is 3. So 1 to 3. So the question was not find the surface area, it was set up an integral in this form. Bang, and that's exactly what we've done. We've set up an integral in this form using Cartesian coordinates. Okay, so the second part's going to be polar. Before I do that part, are there any questions so far? A question about this. I'm always going to take questions about the example I do before moving on to another example. But you're all happy with that? Okay, so the second part, which even says hard on it, in parentheses, is to do the same integral in polar coordinates. Now, what that involves is nothing other than taking this integral here, in either of these forms, and changing it to polar coordinates. So it's not like we have to do any more surface area stuff. We already have a double integral in Cartesian coordinates, and we're just starting to do it in polar coordinates. So unfortunately, it is hard. And the reason it's hard is because this circle is kind of an unkind circle. Now, I have a question. Did you ask me this question specifically for the second part, or did you, like, as in, you know, you asked it to me. I'm just curious. Did you get up to this point and then get stuck on the polar, or did you want to see the whole thing? The polar, right. So that's what I thought. Yeah, it's difficult. So here it is. When you're working in polar, you have to do this. You have to take a ray, a fixed theta ray. So here's my which is this length. And you also have to work out where is the R out, which is this length. So remember that you're sort of firing a bullet and it goes up and it gets into the region and then it comes out of the region. So you have to do some geometry to do it. Now, unfortunately, in this case, the geometry is pretty nasty. So I'll need a different picture to work out what's going on. Okay, so this length is 1, this length is 1, the radius is 1. This angle here is theta, and I'm going to draw that triangle so that this is 1. All right, so I'm afraid that in order to find this length, which I've called R in, you need to use the cosine rule, or the law of cosines, which you don't remember, I suspect. So if you don't remember it, you are screwed. You can't do the problem. Okay, you can leave it blank, you know. Okay, so basically, you have this triangle, right? What?
I'm sorry, there's a spider on my paper.
Oh. How did it do? Better than you? Just kidding. Is it? I mean, I come from a land, well, it's down under, I guess, but I come from a country where the spiders are actually dangerous. So when there are spiders here, they're just wussy little spiders. You'll be fine. You'll be fine. 10 most dangerous spiders are in Australia. It's true. Same with snakes. All right. Are you embarrassed enough? Good. No, it's totally cool. It's totally cool. Okay, back to cosine law. All right. I'm sorry, I didn't mean to embarrass you. Okay, now take this. Take this. Okay, everyone, please, please. Okay, so we've got a triangle of length 2. One of the side lengths is 2. The other side length is 1. And we have to find, well, this one, 1. And actually, the other triangle has the same properties. If you are doing R out, then we have 2, 1, and R out. So basically, that's the situation. We've got angle theta, 2, 1, and we need to find R, which is either in or out. Okay, so what is the law of cosines? Does anyone remember it? Okay, let's write it out, since we haven't seen it for a number of years. Here's A, here's B, here's C. So what is the law that we need? Oh, wait, she's got it. C squared equals A squared plus B squared minus 2AB cosine theta. Now, the part of the justification for asking a problem like this, or why you might be expected to know it, is because we did actually see the law of cosines in this course. This is the dot product, twice the dot product, and it came up right at the beginning in that context. Anyway, here we have A equals 2, C equals 1, so we have 1 equals 4 plus, and B is just R. R squared minus 2 times A, which is 2, times B, which is R, cosine theta. And we need to solve that for R. So it's just a quadratic equation, and if we simplify it a little bit, we have R squared minus 4 cosine theta R plus 3 equals 0. And it's not particularly nice because we don't know what cosine theta is, So we just have to use the quadratic formula. And you get r equals minus b plus or minus the square root of b squared, which is going to be 16 cosine squared theta minus 4 times 3 times 1, which is 12. All that divided by 2a. And it's kind of nice to simplify that a little bit. I'm just going to divide by 2. So it's 2 cosine theta plus or minus the square root of 4 cosine squared theta minus 3. I've pulled out a 4. When you take the square root, it becomes 2. So these are the two possible values of r corresponding to r in and r out. And so r in is the minus, of course, because it's smaller, and r out is the plus. And so when you finish, you can now convert to polar coordinates to describe r, the region, capital R. You say theta, well, you say r goes from 2 cosine theta minus root 4 cosine squared theta minus 3 to 2 cosine theta plus root 4 cosine squared theta minus 3. Okay, the only thing left to say is, what is the total range of theta? Okay, so before I do that, let me set up how the integral is going to look. So the integral we want, so our integral, or surface area, I should say, is equal to double integral. Let's just look at this. The easiest part of this is to change 4x squared plus 4y squared into 4r squared. So in r terms, this is going to be 4r squared plus 1, and then we're going to have r dr d theta. That's always, don't forget that r there. And we've decided that r goes from 2 cosine theta minus root 4 cosine squared theta minus 3 up to 2 cosine theta plus root 4 cosine squared theta minus 3. It's ugly. It's really ugly. But to finish it, we need to know what is the range of theta that we can possibly expect. So, in other words, back in this picture here, the first theta that you see is down here. We're going to use a negative theta, sorry. And the last theta that you see is here. And luckily it's symmetric, so we only need to work out one of them. Okay, so maybe I better take one more diagram over here just to tidy things up a little bit. So what's this angle? That's what we have to work out. That's the only thing left to work out. This is 1, 1, 1, and this time it's a right angle. So here's our theta. So this is 2. So sine theta, at the very last place where it's relevant, sine theta is a half. So theta is pi over 6. And then by symmetry, this theta is minus pi over 6. And so this integral is going to go from minus pi over 6 to pi over 6. Okay, that was pretty hard. Okay, so that I kind of rushed over that. Look at the r in triangle. It has an r in, it has a 2, and then the opposite side is 1. Now what about the r out triangle? It also has a 2, the opposite side is 1, and this is r. So the two solutions you get from the cosine rule, one of them is r in and one of them is r out. And the smaller one has to be r in, because you hit it first. Okay, so one of them is the minus, and the other one is the plus. Okay? So luckily you only had to do it in one step. Yeah?
Instead of doing the law of cosine, can we just plug in r cosine or r sine theta into the original equation?
That's a good question. So the question is, instead of using the law of cosines, could you not say, well, we know that y goes between this and this, right? The original equation, right, which is essentially this. Right? No? Yeah, I mean, if you plug in x equals r cosine theta and y is r sine theta, into there, which you know what it is, and then solve for r, you will, yes, you could square both of these, or yeah, I guess you could put it in there and you would get the same quadratic equation, or you should. So you're right, you don't necessarily even need the law of cosines. You can effectively prove the law of cosines in this special case by plugging that in. So yes, I agree, you can definitely get away without using it. But it's kind of cool. Yeah, does everyone see what I'm talking about? Do you want me to sort of show that little aspect of it? Anyone? No? You? Do you? Yes? Okay. It won't take very long. And it's a really good suggestion, and I confess I didn't think of it. I confess I didn't think of it, but it's the algebraic version of this as opposed to the geometric version. So we know from our previous things, our previous discussions, that y squared plus, well, what is it, x minus 2 all squared plus y squared is less than or equal to 1. So if you just plug in x equals r cosine theta and y is r sine theta, and to hell with the geometry of it, then you'll find you probably get the same quadratic. You get r cosine theta minus 2 all squared plus r sine theta is less than or equal to 1. So if you simplify this, you get r squared cosine squared theta minus 4 r cosine theta plus r squared sine squared, well, plus 4. Look, it's going to be the same. It's going to be exactly the same. This and this gives a squared, and it's exactly the same. You find the two values of r that solve the thing. It's the same quadratic equation. So a very good suggestion. Saved us quite a lot of geometry, and it followed right directly from the Cartesian. So I like it. I like it. But it's nice to know that you have two methods. All right, any other questions about this example, any aspect of it? All right, so I believe you are next. So if you know which exam it is, I can... All right, while you're bringing that up, I'll clear a little space. Okay, so we don't know what year this is from, but maybe someone will spot it. Okay. Here goes. Please. Let S be the surface defined as follows. X squared plus z squared equals 4. And we're given that z is less than or equal to 0, and also that minus 1 is less than or equal to y is less than or equal to 1. And also f, a vector field, is given by xzi plus xyj plus 3xzk. All right, so part 1 says compute the curl of f. So that's the easy part, presumably. Haven't looked at part 2, but we better just do the first part. So part A, find curl f. So we set up our determinant, I, j, k, d dx, d dy, d dz. And then we have xz, we have xy, and 3xz. Yes, that's it. All right, so the I coordinate is the y derivative of this minus the z derivative of this, which is 0. The j coordinate is the x derivative of this, which is 3z, minus the z derivative of this, which is x, but then we need a minus in front because it's the middle one. And the k coordinate is the x derivative of this, which is y, minus the y derivative of this, which is nothing. So I get 0, x minus 3z, y. Now that's not exactly what you had here, but you just, you had x plus 3z, but the previous line was minus 3z minus x, so just careful when you do this distributive law thing here. It's a strange thing, but you know, if you get, this is a sort of place, and you know, I'm picking you out because I see it on the paper here, but any of you, this is the sort of thing where, okay, if you get this curl wrong, then probably the second part won't work out or you won't be able to do it. Or a lot of the time, a small computation error can completely screw up the question. And it's sort of a shame, because if you actually know how to do all your Stokes and your Green stuff, and then you get stuck on the computation. So basically, it's a plea to be really careful. The problems, and you may have noticed that a lot of the solutions to problems are very short in the answers. Sometimes they've left out some details, but you shouldn't really be writing a lot for most of these problems. So it's really, really important to get all the details right. In any case, the second part says, let C, okay, so there's the x, y, and z axes. We're looking at x squared plus z squared equals 4, which is a circle in the xz plane of radius 2. So in some sort of perspective, it looks like this. That's just in the xz plane, but of course, since y is not specified, you actually get a cylinder. But we only need the bits of z less than or equal to 0, which is actually not the top half of the cylinder, but the bottom half. And what's more, we only need the bits where y is between -1 and 1. So all in all, the thing looks something like this. So it's just the bottom half of a ring. Okay? I mean, it's the whole cylinder. Well, I think I was doing better before. Never mind. There it is. I drew an extra line around the middle of it. But you can see it's just half the cylinder. The chalk makes it look a little more messy than it really is. That's my excuse anyway. I'm sticking with it. All right, so it's the bottom half of the cylinder. Now, you are supposed to say, let C be the boundary of S oriented counterclockwise when viewed from above. So you've got to look at this little ring. That's what it looks like, okay? It's just my cupped hand. This is the Y. So the boundary is going to be this flat part here, and then the two curved surfaces and the other flat part. So there's another flat part. Here's a curved surface. And here's one of the curved surfaces. And we're supposed to go counterclockwise when viewed from above. So that means if we're looking from above, you've got to go this way. All right. And the question is, find the work done by F along C. All right. Yes?
Even though our circle is like flattening the XZ plane, above is still the Z.
Even though, I'm sorry?
Even though like we had our kind of circle in the XZ plane and it was extending the Y, above is still the Z component. Is Z always going to be like looking from above? Or can
we always consider Z as being from above, yeah. Okay. Yeah, so I mean, there's certain ambiguities in language compared to showing a picture of it, but I think in this case it's pretty clear. I mean, that it has to be this way and not the other way. Like, I don't see how you could possibly interpret it the other way, although I've seen exam questions which are more ambiguous than this. So in particular, even if you look at it from this way, It's still counterclockwise. It's only if you actually get your head underneath the thing that you'll get it wrong. So unless you, from any direction where x and y and z are positive, I think you'll get the correct orientation there. All right, but I do want to stress, and it's not clear from the diagram, that this is in the xy plane. It's just not obvious at all that these are in this line z equals 0. It's not very well drawn. The whole thing should be pushed down a little bit in a way, or the x and y axis should be pushed up, but what can you do? So in particular, this axis goes through this point and this point. Okay? So the question is to find the work done by F along C. Now, the first thing to realize is that a work integral is like this. F dot dr. And this is a closed loop. It's a messy closed loop. It has 4 different segments. So my question for you is, what theorem are we going to use to deal with this work integral here? Stokes' theorem, okay? We cannot use Green's theorem because it's not in a plane. We cannot use the divergence theorem because the divergence theorem involves a surface integral and a volume integral. And we have a line integral. So almost by process of elimination, all we're left with is Stokes. So according to Stokes' theorem, if you have a curved surface or any sort of surface like this that's orientable, then this is equal to the double integral along the surface of the flux of the curl. So you take curl F dot n d sigma. Okay? Now, the other little hint is that you know Stokes' theorem, I always remember, circulation or work done by F is equal to the flux of the curl. The flux of the curl. Stokes, flux of the curl. Remember that and you'll be in good shape. So actually the fact that they asked us to compute the curl was in and of itself a subtle hint to use Stokes' theorem. All right, so that's just good exam technique to be aware of these little things. You know, they're not just capriciously asking you to find the curl. I guess they could to confuse you. It's possible, but I haven't seen it. Okay, so now what are we on about? We need to tell what n is. We need to say what n is, and this is sort of important. Which unit normal is it? Okay, so we got to use the right-hand rule or my look left rule. So the right-hand rule looks like this. You pick a piece of the thing and you wrap around and you go through until you pierce the surface. And then you see whether you're going, which way you're going. So bang, I'm coming out behind it and up. So the normal that I want comes up. It's sort of hard to draw, but I want always the upward normal. Okay, look what would happen if I used my left hand instead. So I put my left hand, say, on this part of it, and I go through, in which case it would be indicating the downward normal. So you can't use the left-hand rule. The other way of saying it, there's a lot of chatter over here. I'm not fond of that, so if you could just stop it. Thank you. So the other way that I was saying is that you walk along the surface so that it's to your left, and the trees have to be up, as in the normal has to be going up the same as you. So if you imagine yourself walking along so that the surface itself is to your left, which means this way, then you want the normal to point in the same direction as you. Okay? So when you're over here, if you want the surface to be your left, you have to actually walk upside down. Walking along, but the trees are going to point that way then, upside down. So I don't know, it's sort of, actually no, I don't know what I'm talking about. If you're walking this way, the surface, you still are correct, but you're the correct way up, and then the trees are like this next to you. It's sort of hard to explain. You kind of have to just visualize it. You find that the surface is always to your left and the trees are always pointing up. Anyway, so it's important to notice that we're going to need upward, as in positive z, unit normal. Otherwise, you'll get the negative of the answer that you're looking for. All right, so we've computed the curl. And now we just have to do the work. We just have to do the work. So let's see, the equation of the surface was x squared plus z squared equals 4. And so z is equal, well, let's just leave it like that for the moment. We'll call this f. And so we have grad f is 2x, comma 0, comma 2z. And in particular, the grad f dot k is just 2z. All right, so according to what I have said earlier, d sigma is the length of grad f over the k component absolute value. Now, for reasons of just being clever, I'm not going to even bother expanding this grad f. Instead, I will take grad f dot k and put that in absolute values. And we want this dA. I forgot the dA here. All right. We also need what the normal is. We need to find the normal. And as per my previous sort of description yesterday, the normal is plus or minus grad f over its norm. So it's plus or minus 2x, 0, 2z over the norm of grad f. And again, I'm not going to touch that. So now we have to ask ourselves, is it plus or is it minus? And this is the tricky part, or this is one of the tricky parts of this problem. So we need to choose the normal that points in the correct direction, namely up, when we're there. So for the values of x, y, z we care about. Okay, so the question is, it's either plus or minus. That's just two possible answers. Multiple choice. Okay, show of hands. Who thinks it's plus? All right, who thinks it's minus? Who doesn't think? No one? Good, good. Actually, it's minus. Mostly wrong. Okay, why is it minus? What do you want the z component? What do you want the z component to be? Positive or negative? Positive. What's z? Is it positive or negative? It's negative. So z is negative. So you need the minus. So we need minus 2x, 0, 2z over grad f. Now, it's no crime to replace grad f by square root 4x squared plus 4y squared, but we know that they're going to cancel out anyway. So now it's time to assemble this integral so we can compute it. By the way, let's come over here. How do I simplify 2z, absolute value? What's the correct thing to get rid of the absolute values? Negative 2z. Well, you're excused. The absolute value of a quantity is plus or minus that quantity. It's plus if the quantity is positive, and it's minus if the quantity is negative. For example, what's the absolute value of minus 5? Well, 5. Think that as minus 5. Okay? It's a good little thing. If you're taking the absolute value of something that you know is negative, it's minus that, because after all, negative minus a negative is positive. Okay? So careful of that. All right. Here goes. We are... Okay, we're dealing with this. We're dealing with this. What's the curl? Well, we just computed it as 0, x minus 3z, y. And we computed as negative 2x, 0, negative 2z over the length of grad f. And the reason I didn't bother computing it is that d sigma is the length of grad f divided by minus 2z, and this is going to be dx dy. Now, if you didn't get the minus here because you mistakenly thought z was positive, and you just drop the absolute values, and you also forgot about the minus here, then you would have been okay in terms of the final answer because the minuses cancel out. However, that is just pure luck, and you may also not get the full points for it. Anyway, we need to do a little bit of work. Okay, come on, please. I know the final's coming up, but come on. The question is, does it not usually happen this way? You know, I don't know whether it usually happens that way. I haven't seen enough examples where these things are going like that. Basically, my gut feeling is that it will often happen that if you get one wrong and the other one wrong, then they will cancel out. But I wouldn't want to take the risk. Also, I wouldn't give it full credit. I wouldn't give it full credit. I mean, z is negative. You're supposed to deal with that. So, you know, I mean, the only way I give it full credit, I mean, the alternative is to just say, I don't even know what it is. I'm just going to take the absolute value, and I guarantee that's going to have the right direction. So then you might get away with it, but and then because the absolute values will cancel out. But best to be careful and do it properly, and not take any chances as to whether these things cancel out or not. Anyway, the dot product, 0 times minus 2x is 0, 0 times x minus 3z is 0. So actually you would have been fine if you left it as x plus 3z as you had on the paper. It's not going to make a difference. So anything I said about it being impossible to do, not only is that false, it's irrelevant. But we do have y times minus 2z. So all this works out to be, and these cancel of course, and this is over some region R, which we're going to have to look at in a few seconds. So we're going to have y times minus 2z divided by minus 2z dx dy, or dy dx. And my question is, what is the region? We now have to finally 1 to 1, that was given. And so where does x go from? Well, it goes from negative 2, that's the intercept there, to positive 2. Right? Because the curve is x squared plus z squared equals 4. So x, the smallest it can be is negative 2, and the biggest it can be is 2. So this integral is just from minus 2 to 2, and minus 1 to 1. And it's very easy to do. In fact, it should be just 0, I suspect. You have the integral, we can split it up into a dx, y dy, and this has got to be 0. I can tell because y is an odd function, and I'm going from minus 1 to 1. So you will find that this is 0. Okay, are there any questions about that example? Yes?
Will we ever have to do a shadow that's not on the xy plane?
So the question is, would you ever have to do a shadow that is not in the xy plane? I haven't seen it in the past finals that I've looked at, but it's conceivable. So the question is, what if, for some reason, you need the shadow on another plane, say the yz plane? Well, imagine that that curve was tilted so that it was this way, and then the shadow, if the curve was sort of vertical like this, right, then the shadow would just be a curve, and that's no good. So that there'd be no way to salvage that situation. So the point is that this formula here, the k is the z coordinate. That is because you are projecting down onto z equals 0. So you would change it to j or I, and then you would have to just, you know, do it that way. And the rest is the same, as long as you interpret r as the projection. And then the dA wouldn't be, say, dx dy. It might be dx dz if you're projecting onto the xz plane. So you should be adaptable, but then again, I've never seen a problem that involved it. So it's just an extra level of sophistication to change x's and y's around and use a different component. I would be surprised to see it, but it's possible. Any other questions about this one? About this one? You can go next for the next problem, but I kind of want to just clear up any lingering questions about that. Doesn't sound like there is, so let me clear some board space. Cool. Okay, I'm going to do. Well, maybe I have to do the whole thing anyway. So I'm going to do the whole thing. There's part A and part B. The reason I'm going to do part A is because it will help you clarify part B, even though you actually don't need to do it. Here's the question. Okay, so it's number 7 from January 2006. And it says you have z is x squared plus y squared, which is a paraboloid, and you want the part between z equals 4 plane and z equals 16. Okay, so it's our same favorite paraboloid that we've seen already, but we just need the part between 4 and 16, and it's just that part of the surface. Okay? Not a problem. And this first part is to find the area of S. And then the second part is to use the divergence theorem. So let's just find the area of this, since it's probably not too bad. And it's yet another one of these surface area things. So to find the area, we've sort of done a similar problem a few days ago, as I recall. All we have to do is compute. So surface area is the double integral of 1d sigma over S. And so we're going to, again, let f be equal to x squared plus y squared minus z. And once again, and so that's supposed to equal 0. And once again, grad f is 2x, 2y minus 1. And its length, this is just a duplication, 4y squared. This is a very familiar site here. The k coordinate is just minus 1. And its absolute value is 1. So this is just replicating what we did before. There's a slight difference when we actually compute it, because the region is different. So what we have is we have the shadow d sigma, same formula. So again, it's root 4x squared plus 4y squared plus 1 dx dy. And so when you compute this, the d sigma part is 4x squared plus 4y squared plus 1 dx dy. Okay, so that's the integral we're looking for. We just have to identify r, and if you think about it, when you project it down, the shadow is a circle. This is height 4, but the circle is x squared plus y squared equals 4. So it's from 2 to 4, right? Okay, so just to be precise, when z equals 4, we're dealing with x squared plus y squared equals 4. So that's radius 2. And when z equals 16, this equals 16, and so that's radius 4. So r is actually x squared plus y squared between 4 and 16. So obviously we're going to use polar coordinates here. So in other words, r is between 2 and 4, theta is between 0 and 2 pi. This integral is just 4r squared plus 1 times r dr d theta. And this is not so hard to do. So I'm going to leave the rest to you. The substitution, you see, the derivative of 4r squared plus 1 is just 8r. And I did this actually yesterday. I did the same integral with a different range of r here, but, you know, I'm not going to do that again. So anyway, the real meat is in the second part of the question, which is tells you to use the divergence theorem to compute a certain thing. So we'll see what that is in a few seconds. So what happens? We're given a vector field, which I will write up in just a moment. All right, we're given f is equal to x plus z squared e to the x plus y 3 plus z. And we want to find bless you. We want to find this this integral here. Now, this is a flux integral, and I'm reproducing it as it is on the paper. They've been a little sloppy. It should really be this. But, you know, I don't think there's much ambiguity. I have to say that mathematicians will often write down surface integrals without the double integral, figuring that, hey, what else could d sigma be? It's obviously a surface element, so let's not get too caught up about that. If you do only see one integral like that, then don't think it's something fancy. It's just an omission. All right, so anyway, we're supposed to find this. And we're given that n is the outward pointing normal. Okay, n is the outward pointing normal. So if we go over here, all right, so the question is, given that n is the outward pointing unit normal, like that, find this using the divergence theorem. Okay, what do you need to be true for the divergence theorem? What's an essential thing about your surface? It has to be closed. Is this closed? No, it's got a top and a bottom missing. So the first thing you have to realize is that you have to let S1 be the top and S2 be the bottom. So let S1 be the top, S2 be the bottom. So what is the top? Well, the top is at height 16, and x squared plus y squared is less than or equal to 16. That's this circle here. Whereas the bottom is z equals 4, and x squared plus y squared is less than 4. Now, you also have to extend the normal to both the top and the bottom. And it has to be the outward normal in all cases. So when you're on the top, what is the normal? It points straight up of length 1. So here, the normal is just k, which is 0, 0, 1. It doesn't matter where you are because it's flat. So you could compute it by writing, hey, z equals 16, grad is 0, 0, 1. Okay, there it is. No problem. But what's the normal on the bottom? So we've called this S1. This is S. Here's S2. If it's going to be outward to this, it has to point downward. So here, the normal is 0, 0, minus 1. That's the unit normal when you're on the bottom. Okay, so to set up the divergence theorem, we're going to consider the complete thing, S, S1, and S2. And I'm going to write this equation. Okay, so this is now a closed surface, and you might want to just say, since, well, we'll fill in the right-hand side, since S1, S union S1 union S2 is a closed surface. But what is that equal to? What does the divergence theorem say? That the flux integral of a vector field through a closed surface with outward normal equals what? The triple integral of the divergence of that vector field over D, where D is the interior of this closed surface. All right, this is what we want to work out. And it's difficult to work that out because the surface is sort of curved. It's a mess. So this formula allows us to work out three things which are simpler, hopefully, in order to get our hands on the more difficult thing. A question?
Can we not be told to use the divergence theorem? Can you tell me how to see quickly that it's hard to compute and that I should go for the divergence theorem?
All right, so the question is, how could you see that it's hard to compute? Well, you couldn't see it necessarily. What you would do is you would say, okay, what is the normal? What is n? Well, n is this, 2x, 2y, minus 1, although you've got to make sure that it is minus 1 that you want. Yes, it is, because notice these vectors are all pointing downwards. So the normal would be this divided by its length. But whatever the length is going to get rid of in the d sigma, you have to dot that with the function, with the vector field. And then you're going to have to do a double integral of this form. So look how nasty that vector field is, and look how horrible that is going to be when you dot it. So I would just say try it and see. Now the other thing you might think of is it's not a closed surface, so surely I can use Stokes' theorem. Okay, can someone tell me why you probably can't use Stokes' theorem, why can't you use Stokes' theorem to compute that? Anyone have any idea? If you do, okay. Yeah, Stokes' theorem gives you the flux of the curl of something. This is not a curl. You would have to express f as the curl of some other g. So you have to sort of anti-curl that. Yeah, it's too difficult. So divergence theorem is our only hope, really. Question?
When you're trying to find the d sigma for the flat surfaces, aren't you going to end up dividing by 0?
Okay, so the question is, when you find the d sigma for the flat surfaces, aren't you going to divide by 0? Well, I claim that the answer is no, and in order to show you, I'm now going to compute these three things and finish off the problem. So here they are, three things. 1, 2, 3. We'll do them in that order. Okay, let's look at this. Okay, so for the surface, which is essentially z equals 16, or a part of the plane z equals 16, if we let f just be equal to z, then grad f is 0, 0, 1. So in particular, it's almost pointless to think of this as a surface integral. But if you did want to do it, the k coordinate is 1 and the length is 1, so d sigma is just dx dy. So you don't divide by 0 because the k coordinate is 1. Okay, so that's the answer to your problem. So in any case, this is quite straightforwardly equal to the shadow of x squared plus y squared less than or equal to 16. I mean, the fact that we're on the plane z equals 16 doesn't really do much with the shadow. Everything is very straightforward to write down as this. F dot n, well, here's the f, x plus z squared e to the x plus y and 3 plus z. You have to dot that with the normal vector 0, 0, 1, and it's just going to be dx dy. Because, again, the length of grad f is 1 and the z coordinate is 1. So there's just a 1 over 1 here if you do it fully. But in any case, this is equal to the integral over x squared plus y squared less than or equal to 16 of 3 plus z dx dy. But what's z? On this surface, z is 16. But z equals 16 everywhere on that surface. So the field is really 19. Now you could use polar coordinates, but what is that double integral? It's the integral just dx dy of x squared plus y squared less than or equal to 16. What does that represent? A circle, radius 4, the area. So you just use pi r squared. So this is 19 times 4 squared pi. Okay, I'll just leave it as that. 19 times 16 pi. Okay, so are there any questions about how I found the first one of those? The point is that the vector field is extremely simple. In particular, its z-coordinate, which is all we care about because we're dotting it with 0, 0, 1, is just 3 plus z, but in fact is just 19 everywhere on that surface. All right, so now we've got to do the bottom. It's almost the same. So for the bottom, this time n is 0, 0, minus 1. So you're going to get the double integral, this time over x squared plus y squared less than or equal to 4, of minus 3 plus z dx dy. The minus came from the minus 1. That's important that That's where you really need the negative normal. Whoops. This time z equals 4. So this is minus 7. Z equals 4. So this is minus 7 times the area of a disk of radius 2. So it's minus 7 times 2 squared pi, i.e. minus 28 pi. Okay, so any questions as to how that came about? Yes?
Just check, to get the normal, you took the gradient of the what?
Yeah, I mean, look, to get the normal in this case, I just looked at it and saw what it was. But I mean, I'll show you how you can get it using the standard method. Okay, so the surface is just z equals, say, 16, or z equals 4. So we'll call that f. The gradient of f is derivative x is 0, derivative y, and derivative of z is that. And then that happens to have length 1 already, so you don't even need to divide it. Okay, the k coordinate is 1 as well. So when you just take the length over it, the d sigma is just 1. Okay, but the normal is plus or minus this. Okay, and then you have to look at it and say, oh, when it's the top piece, it's plus, and when it's the bottom piece, it's minus. There's no mathematical to do that. It's really a geometrical. There's no computation, rather. It's a geometrical thing. All right, so S2 is very similar to S1, but you get a negative instead. Anyone know what 19/16s are? 304? Okay, thanks. 304 pi. All right, we still have one more piece to do. We have to do the divergence piece. So we're going to come back to this vector field f over here and compute the divergence. Div f is, you take the x coordinate over here and take the x derivative plus the y derivative plus the z derivative. The x derivative is 1, the y derivative is 1, and the z derivative is 1. So it's basically 1 plus 1 plus 1, which is 3. So the triple integral we're looking for is just 3 dv. dv is dx, dy, dz. And we've got to integrate over this region. So the region is the, come back over here, sorry to make you pan so much, but the region's the interior of this. So I guess I will write it in Cartesian coordinates as just x squared plus y squared has to be less than or equal to z, but z is between 4 and 16. So it's going to be hard to compute like that. We need to use what coordinates? Cylindrical. Yeah, it's cylindrically symmetric around the z-axis. So you asked me, I think, earlier about whether we ever need to do projections onto the onto xz or yz. You also could ask along the same lines, hey, do you ever need to do cylindrical coordinates where instead of z as being the z and the other x and y be r cosine theta and r sine theta, why not let, say, x be x and y be r sine theta and z be r cosine theta? You could do that. There's cylindrical coordinates. But somehow these problems are normally set up so that the z-axis is the axis of symmetry. So I'm going to use cylindrical coordinates and write this as the 3 can come out. This is going to be, in cylindrical, you have something like dz r dr d theta. Now, this will be the most useful thing if, for fixed r, you have a nice value of z. But that's not what you have. If I fix r theta, meaning a point on the xy plane, then the z is different over here than it is over here. Here the bottom is flat, the top is flat. Here the bottom is curved and the top is flat. So I kind of think that you could do it that way, but it's best actually to realize that you can just switch it around to r dr dz d theta. Now the benefit of that is, coming back over here once again, is you fix a value of z and theta, and you ask yourself, where is the r? Where is the r? So as in, r starts at 0, but where does it come out? Well, it comes out when x squared plus y squared equals z, right? That's the equation. And this is r squared. Right, so the in is 0, and we come out, when we're at a height of z, the time we leave is when r squared equals z. Well, that means r is equal to root z. So in this equation, or in this integral here, r is going to go from 0 to root z. Z goes from 4 to 16, and theta goes from 0 to 2 pi, because we're covering the whole thing. So that's how you've got to set it up in cylindrical coordinates. The tricky part is this root z here. Again, we need x squared plus y squared. Here it is algebraically. X squared plus y squared less than or equal to z. So r squared is less than or equal to z. So r has to be between 0 and root z. And there it is. R goes from 0 to root z. Okay, I better compute this. So the 2 pi d theta can come out, but the rest of it we have to kind of do properly. The integral of r is 1/2 r squared, but luckily we're going from 0 to root z. And I'll pull out the d theta. So we get 3 times 2 pi times 1/2, and then when I plug in root z into this, you just get z. So it's the integral from 4 to 16 of z dz. Can this camera see, can you see down there? Okay. So you get 3 pi. This is all very straightforward now. The integral of z is z squared over 2 from 4 to 16. And so I get 3 pi over 2 times 16 squared, which is 256, minus 64, which is, no, 16, thank you. It's not 8, so it's 240 divided by 2. Did I make a mistake? 240 divided by 2 is 120 times 3 is 360. 360 pi. Okay, so, sorry. The last part is once you get down to here, it's fairly straightforward. I probably got it wrong, but there you go. 360 pi. Okay, any questions about that divergence part of the integral?
So when you change the order, you're holding r constant?
Okay, so I wrote it in this order. The way you always work from the outside. So first of all, I hold z and theta constant. So I'm going to pick a height and some ray, and I'm going to see where does r start and where does r finish. So you're starting at 0 and you're coming out at root z. Okay, then I can free up z and fix theta.
Right.
And z is going to go from 4 to 16 no matter what theta is, and then theta goes from 0 to 2 pi because it's the whole thing. All right, any other questions about that divergence integral part? Okay, so to finish the problem, you come back over to this equation and you just fill in, this was 304 pi. This, we found, was minus 28 pi. And this was 360 pi. So all you have to do is throw everything on the other side and you find, and of course you'd have to write this out on another equation, but I reckon that if you've cancelled this out, you get 56 plus 28, which is 94 pi. Is that correct? What? Did I get it wrong? 84. I can't add 28 and 56. There you go. 84 pi. Is that what the answers say? Did they have solutions for this or not? Did they provide solutions for this exam? Does someone have them? No? Might as well check it, right? It's right? Okay. So there you have it. This, my friends, is a tricky problem. You agree? I mean, this is... First of all, you have to get the divergence theorem part and add those two surfaces. And then you have three things to compute. And let it be said that they're not three of the most difficult and messy things, and yet each one of them has a little bit of a twist to it. All right, so that's... I kind of say to you that that's a hard problem. Okay, I say this to you unabashedly. Now, what was it worth? It was worth a measly 16 points, whereas the previous one was worth 20 points. So I kind of think that was a little bit mean to only give it 16, but that's what they thought. Are there any other questions about that example specifically? All right, so who else wants to ask a question? Forget integrals, forget anything other than pre-midterm stuff. Yes, you do have to know this stuff, and here is a nice juicy problem from there. It says, this is number 1 from, is it spring 2007? Is that what I'm... Yeah. Let z be the sphere, x squared plus y squared plus z squared equals 15. I'm sorry, let S be that sphere. And L is the line. X, Y, Z is 5/16/2007. Yes, that was the date of the exam. So, let's see, 1,26/2008, that might come up. Okay, so, all right, so it's 5/16/2007 plus 1, minus 1, 0, t. Okay, so there's that line, and it says, find all planes tangent to S that pass through the point P, which is 2, 3, 5, that do not intersect L. Okay, so it's a sort of interestingly and slightly differently worded question, but there you have it. Okay, so let me ask you this. If you have a plane and you have a line, and you know that the line doesn't intersect the plane, what can you say about that line? Well, it has to be parallel to the plane. It has to be parallel to the plane. You see, you might think, couldn't this be the situation? But of course, the plane keeps on going, no matter how much you draw of it. So unless the line happens to be exactly parallel to the plane, meaning parallel to some line in the plane, not every line, but there's lines in the plane along this direction that go in the same direction, such that this line is parallel. Now, by the way, just knowing that it's parallel to the plane doesn't quite is the plane, but it could actually be lying in the plane, in which case it's intersecting infinitely many times, right? But if it's going to only intersect once, that will happen whenever it's not parallel. A question?
Two lines which are parallel like this will have the same right part, right?
The question is, if two lines are parallel, they have the same right part. Or it could be a... No, if they're parallel like this, they're not really parallel, they're just not intersecting. They're called skew lines there. So if two lines are actually parallel, then this vector either has to be the same or a scalar multiple thereof. But anyway, that's not relevant. Nothing to do with this problem. Okay, so the first thing to realize is that whatever plane you're looking for has to have a line parallel to this. Now let me ask you that. What's the easiest way to describe a plane? How are we describing planes? By the normal vector. And if the line is parallel to the plane, then it's perpendicular to the normal. Okay, so whatever plane we're looking for, any plane that we're looking for, our plane has a normal n, which is perpendicular to the vector of the line, which has got nothing to do with the 5, 16, 2007, has everything to do with this. 1, comma, minus 1, comma, 0. Okay, so that's the first thing to observe. And it's kind of nice. It's kind of nice. So the next thing to do is to try to find the general equation of a plane on this sphere. So rather than use little x, little y, little z, you could use a, b, c. I'm going to use, I'll use a, b, c. What the hey? Actually, you know what? It's probably better to use capital X, y, z. So at the point capital X, capital Y, capital Z on the sphere, what is the tangent plane? Well, the way you do this is similar to the way you find a unit normal, right? What is the tangent plane, I should have said? Well, the normal is equal to the gradient of f, if you like, divided by its magnitude, but that's not really that important. And maybe it's plus or minus. Hey, it's the same formula that we had before. So what is f? Well, f is equal to x squared plus y squared plus z squared, which happens to be 15. As long as it's constant, that's fine. And grad f is equal to 2x plus 2y plus 2x comma 2y comma 2z. So actually, you don't even need a unit normal. You don't need a unit normal. You just need a normal. You just need a normal. So you could even divide that by 2 and just say a normal at capital X, capital Y, capital Z is also capital X, capital Y, capital Z. But it's not wrong to have a 2, and it's not wrong to divide by the normal derivative. That's all fine. So let's just see whether that makes any geometrical sense for a second. So the point is, at the point capital X, Y, Z, normal is also X, Y, Z. And so what is the equation of a plane through a given point with a given normal? It's only for a sphere that the normal happens to be the same as the point. Okay, so let me remind you, yes, here is the equation, so you need to know this. In general, if a plane goes through, say, so plane through A, B, C with normal, say, P, Q, R, is what? Well, it's going to have to be something plus something y minus q, no, y minus b, plus something z minus c equals 0. And that something happens to be p, q, r. Really useful to know that. It just comes from the dot product, of course. But you can tell, as a sanity check, it certainly goes through A, B, C, right? You plug in A, comma, B, comma, C, and you get 0, 0, 0. And the normal is in the direction of P, Q, R, just by taking the gradient of it. Call this G, and then grad G is P, Q, R. Okay, so if you know this, then you can say that the tangent plane is, and I'm going to apply this formula with both A, B, C and P, Q, R equal capital X, Y, Z. So it's capital X, X minus capital X, plus capital Y, Y minus capital Y, plus capital Z, X minus capital Z equals 0. Now, we know something about the normal, though. We know that the normal is supposed to be, perpendicular to this vector 1, minus 1, 0. Before we do that, I just thought I could take this and show you what to do with it in general for a sphere, just in case it comes up. If you expand this out, you get capital XX plus capital YY plus capital ZZ equals capital X squared plus capital Y squared plus capital Z squared, which happens to be 15 in this case because it's a sphere. That's kind of useful in general to be able to write that. But in any case, we know our normal. We've seen our normal, which is not a unit normal necessarily, which is x, y, z. And we've seen this is perpendicular to 1, minus 1, 0. So we also know that x, comma y, comma z dot 1, minus 1, 0 is 0. If the two vectors are perpendicular, the dot product is 0. So, well, I'm bringing it from over here. I'm now specifying because we know the plane doesn't contain the line. So we also know that x minus y equals 0, i.e. x equals y. So that's a nice sort of thing. So any plane with x equals y, or any... Let's just review what we're doing. What I'm saying is if I pick this point, capital X, capital Y, capital Z, if x equals y, then the tangent plane will not pass through that line, as in the line doesn't intersect it. So we've almost finished the problem. The only thing left, actually, is to make sure that the tangent plane passes through the point 2, 3, 5. We've never used that point. So we come back to our equation of the plane, which we saw was x plus y plus zz equals 15, and we need x, y, z equals 2, 3, 5 to satisfy this, because it's got to lie on that plane, and we also need capital X equals capital Y. And there's one other equation. So I'll put that, well, let's see what this first equation is this. When we put 2, 3, 5 in, we've got to get a solution. So 2x plus 3y plus 5 capital Z is 15. That has to be true, because 2, 3, 5 lies on the plane. But also x equals y, so 5x plus 5z is 15, and we've seen that x plus z equals 3. What's the one other thing that we know about x, comma y, comma z? Capital X, capital Y, capital Z. Lies on the sphere. So we also know that x squared plus y squared plus z squared equals 15. And remember, x equals y, so this means that 2x squared plus z squared equals 15. And we just need to solve those equations simultaneously to finish off the problem. This? Well, 2 plus 5z equals 15 because the plane contains 2, 3, 5. We know x equals y because the plane doesn't intersect the line. And then 5x plus 5y is 15. I just divided by 5. So we are going to just finish off this little simultaneous equation stuff. Quite a messy problem in the end, as you see. Quite finicky. A really nasty problem one, if you ask me. Not a gentle introduction to that particular exam. But you got to deal with that. So according to the first equation, z equals 3 minus x. So plug that in the second equation, and you get 2x squared plus 3 minus x all squared equals 15. And so if you expand this, you get 2x squared plus 9 minus 6x plus x squared. These are all capitals. That's 15. So what do I get? 3x squared minus 6x minus 6 equals 0. So divide by 3. X squared minus 2x minus 2 equals 0. And so the solution is going to be x equals minus b plus or minus the square root of b squared minus, which is plus in this case 4ac. So root 12, which is 2 root 3. So x is 1 plus or minus root 3. This also equals y, of course, because we know x equals y. And then z equals 3 minus x, which is equal to 3 minus 1 plus or minus root 3, which we should probably write as 2 minus or plus root 3. And the reason I write minus or plus is to correspond with the plus or minus. All right, so I forget what the wording of the question was. Is it find all planes? Yeah, find all planes. So we have to plug in those values of x, y, z into this equation here. So there's two answers which I will write on this board. The first one is x equals 1 plus root 3. So one plane is this. 1 plus root 3x. And the y is the same. 1 plus root 3y. And then capital Z was, in that case, 2 minus root 3 equals 15. And the other solution is 1 minus root 3x plus 1 minus root 3y plus 2 plus root 3z equals 15. Those are the only possible solutions. Now, that's probably enough to get full credit, but we have been a little sloppy about one thing. There's only one possible extra thing that could go wrong. What is it? Can anyone tell me?
The line is not plane.
Yeah, the line could be lying in the plane. So you want to make sure that the line is not in the plane. Well, if the line is in the plane, then every point on the line is in the plane. What is a point on this line? 5/16/2007. So to really complete it, you should check in both cases that 5/16/2007 is not in either plane. So you just plug it in. You plug in 5/16/2007 and hope that you don't get 15. Well, clearly you don't, right? I mean, it's going to be 5 plus 16 plus 2. It's going to be like 4,000 minus something root 3. And so this is easy to check. And so these are the two planes that are possible. Okay, so before we take a break, are there any questions about that example? It's a pretty nasty geometry thing. Yes, please, just a second. We have one question there and another question there. When we come back, I will respect the order, which is 1, 2, 3. But I have two questions about this, so go ahead.
In a regular tangent plane question,
Yes.
you just plug in, like, would you plug in P into the normal and then dot the normal with like x minus 2, y minus 3?
Yeah, I mean, no matter what the surface is, you can always find the normal by taking grad f. And if you want to make it a unit normal, you divide by that. But that's not so important in this case because the constant can be divided here. So you basically find the gradient of f, and that's the PQR, and then you just need a point A, B, C that lies on that plane.
Plug in the point into the gradient or not? Do you take the gradient at the point?
No, you don't want the gradient. Okay, so the question is, why didn't we never take the gradient at 235? Because 235 is not on the sphere. Okay, you can plug it in and you'll see it's sitting somewhere else outside the sphere. Okay, you'd be kind of screwed if it was inside the sphere, because no tangent plane actually goes through the sphere, right? Something weird with the sound when I'm standing exactly there. So basically, it's only the gradient at the point on the sphere that matters. Okay, so you don't want to take the gradient at 235. And another question up the back. I can't hear.
How do we know that the capital X squared plus y squared plus z squared is equal?
Okay, so how do we know this equation here? Well, because capital X, Y, Z is the point on the sphere that we are considering. So in order to find the tangent planes, every tangent plane corresponds to one unique point on the sphere. All right, so we're going to take a break, but I have some evaluations, and it's very useful for me to find out what I can do better about these things and what you think of the videos, and if you like them, then I can go to the department and say, do them again, and all that sort of stuff. All right, so I'm looking at January 2005, the final, and it's question 5. It says, inside the region where x squared plus y squared is less than or equal to 3 and x greater than or equal to 1, Find the rectangle of maximal area whose sides are parallel to the coordinate axes. So let's just draw the situation. It's a sphere of radius root 3, not a sphere, a circle, radius root 3. Here is 1. And so when we're to the right of x equals 1, but inside the sphere, here we are. Inside the sphere, inside the circle. I'm doing so many three-dimensional things, I can't even say circle anymore. So we're trying to find the maximum area inscribed in there whose coordinates are parallel, whose sides are parallel to the coordinate axes. All right. So this is a sort of either max-min problem or a Lagrange multiplier problem, some sort of thing like that. So in order to change the word problem or the geometry problem into algebra, we kind of need to describe the rectangle. And so the way I'm going to describe the rectangle is to just decide what this point is. So I'm going to call this point x, y. Now if I know that point, then what's this point? X, minus y. And what's this point? What's the x coordinate of that point? It's 1. So this is 1, y, and this point is 1, minus y. So what are the dimensions of the rectangle? What's this side here? Well, it's going to be x minus 1. And how about this side? 2y, because we've got this part of y, we've got, and then, so it's y minus y if you prefer. So the area of the rectangle is equal to x minus 1 times 2y. Okay, so we have to maximize this. We want to maximize this, but we also know, so maximize, what do we know about x and y? It lies on the point x, y lies on the circle radius root 3. So in particular, we know that x squared plus y squared equals 3. So, I mean, you could do this with single variable calculus, as it turns out at this point. I mean, you can solve y for x and all that and then just plug it in. But hey, we've got Lagrange multipliers up our sleeve, so we might as well use them. So the constraint, well, the function we want, I've called it a. So I'm going to call this constraint here. Let g of xy be, say, x squared plus y squared. And so we need g of xy equals 3. So that's the constraint. So when you set up the multipliers, you have dA dx is, say, lambda dg dx. And you have dA dy is lambda dg dy. Yep, you have to remember your Lagrange multipliers. So dA dx is, you differentiate this with respect to x. I mean, if you want, you can just write it as 2yx minus 2y. If you differentiate it with respect to x, so this one becomes 2y equals lambda dg dx is 2x. And as for dA dy, it's just 2 outside of x minus 1. And that's lambda times 2y. So we have those two equations that we have to deal with. All right, so the first one says that lambda x equals y, and the second one says that lambda y equals x minus 1, and we have to solve these things simultaneously. So one way of doing it is to say, let's call this 1, and let's call this 2. And so, provided that nothing is 0, we can solve, so if x is not 0, and by the way, x can clearly not be 0 because x has to be bigger than 1, so, which it isn't, so let's just change this. x is not 0 since we know that x is bigger than or equal to 1. So divide equation 1 by x, and you'll see that lambda is y over x. Now plug that into the second equation, and you get, so in 2, you get y squared over x equals x minus 1. In other words, y squared is x squared minus x. Okay, so that's gotten rid of lambda altogether. We now know y squared equals x squared minus x, but we also know that x squared plus y squared equals 3. So you can solve this together. Y squared I'm going to replace by x squared minus x. And so this becomes x squared plus x squared minus x equals 3, i.e. 2x squared minus x minus 3 equals 0. And I believe this can be factored into 2x x. I'm going to have to put the 3 there and the 1 there, and then I need a minus. So x is equal to 3 halves or minus 1. We reject the minus 1 solution because x has to be greater than or equal to 1. And then y, well, to find y, I guess, what do we know? Y squared equals 3 minus x squared, which is 3 minus 9/4, which is 3/4. So it looks like y is plus or minus root 3 over 2. But if you look at the diagram over here, you'll see we assumed y is positive. It actually doesn't matter. If y is negative, it's just the bottom point. And then the other one's the top point. So, I don't know, what's the question? Find the rectangle of maximal area. Well, the way I describe the rectangle is by the vertices. So, my conclusion is that the rectangle is, well, we know x is 3 halves, y is root 3 of 2. A rectangle has vertices. And I just write out the 4 coordinates. You don't have to put them on separate lines. So 3 halves, root 3 over 2, 3 halves minus root 3 over 2, 1 comma root 3 over 2, and minus 1 comma root 3 over 2. Okay, now how do you know it's a maximum? Well, essentially there's only one. So it either is a maximum or a minimum. But you could just investigate what happens when the rectangle, look at the extreme cases. The extreme cases, in one case the rectangle's sort of like this, but it clearly has very small area, and in the other case the rectangle's like this. Both of those have area much smaller than the one we found, so it must be a maximum. It must be a maximum. Okay, the thing has to have either a maximum or a minimum there. So, any questions about that? As I said, you could actually do this with a Math 103 treatment, but it's, I think they want you to use Lagrange multipliers, so there you have it. I don't think it said anything about Lagrange multipliers, it just says find. Okay, any other questions about that example? All right, so who's next? I can't see her. She's gone, right? Okay. Yeah. Well, then she's, okay. I mean, if she comes back, she can ask it. So you are next, I believe.
Well, can I ask I believe it's January 2007, number 5.
Okay, I think I have that one. January 2007, number. Give an example of a vector field. We better do part A. It says, never mind. Give an example of a vector field f equals n I plus nj such that dn dy, dn dx minus dm dy equals x. Okay, that's part A. This is a very odd question.
What is the question?
The question is, find a vector field in the plane of the form mi plus nj, not New Jersey, such that dn dx minus dm dy equals x. It just says find an example. Okay, you missed your turn, but you'll get it back immediately after this, if you're still here. All right, so here goes. This won't take that long. So the question is, find two functions, n and m, such that that is true. And there's actually a huge amount of choice here, which is what makes it unusual. So does anyone want to hazard a guess? You can make one of them equal 0. Which one do you want to equal 0? M or n? M? Okay, if you set m equals 0, then what's n got to be? X squared over 2. So one possibility is that n equals a half x squared, and then m equals 0. What's another possibility? What if n equals 0, then what? If you prefer n equals 0, what would m be? Negative xy. Okay, that would work too. Or you... Huh? M could be... Okay, so if they're both equal to xy, then that's not going to work, because the first one will give you a y when you differentiate, and you don't want a y. But there are possibilities of having them both non-zero, but why make life more difficult? We'll just go with this one. What the hell? Okay? And if you want to, you can try the second part of the problem with, say, n equals 0, m equals minus xy, which we decided would work as well. And you can add constants to them, to either of them, because the differentiation doesn't make a difference. So the interesting thing there is there's quite a lot of flexibility. So I'll just go with what our gut feeling was, which is this. We'll just go with this when we go into part B. So part B says, use Green's theorem and the vector field you found to compute this. It's the double integral over R of x dx dy, where R is given by x squared plus y squared less than or equal to 4, and x minus 1 all squared plus y squared is greater than or equal to 1. And it says, you must use Green's theorem. Well, that's how I read it anyway. The must is just capitalized, but I guess what that means is you'll get no credit if you don't use Green's theorem. All right, so let's just draw the region. X squared plus y squared less than or equal to 4 is the interior of a circle, radius 2, whereas the other one is the exterior of a circle centered at 1, 0 of radius 1. So I think it's this. So we want everything inside here, but outside there. So it's like a little crescent-y thing, croissant shaped. All right. So for us to use Green's theorem, what we're looking for is this. Now, this looks sort of bizarre. What's the x doing there? Well, where have you seen x before in this problem? You've seen it in part A. So part A, by part A, for our choice of nm, we have this. Okay, so this is because this equals x. This is for our choice of capital N and M, whatever they are. It doesn't matter what you did for part A. That's correct. So then what do we do? What does Green's theorem say? Well, it depends which version. I forget which one I called which. But this is just the line integral of circulation line integral. So this is Green This is not the flux version. This is the circulation version. All right. So that's green. Now this equals, in our case, we decided that m would be 0 and that n would be a half x squared. So just to simplify, it's just 1/2 x squared dy, and we need to find that integral where c is what? This is where the key interest comes. Where is c?
The sum of the two.
It's the boundary of this region. It's the boundary of the croissant, oriented counterclockwise. So I agree that you're going to break it up into two pieces, but which two pieces? Right, so we're integrating r. It needs to be the boundary going counterclockwise. So how do you go counterclockwise around there? Well, you've got to go counterclockwise like this. And then you reach at this point and you do a sharp U-turn and proceed along here. Guess what? That's actually clockwise around that circle, so that when you get back down to the cusp, you turn around and go counterclockwise. So there's a subtle little point there, is that you have to go clockwise around one circle and counterclockwise around the other. So this I'm going to break up. I'll call the outer circle C1 and the inner circle C2. So I'm going to break this up into 1/2 the integral of C1 going counterclockwise plus C2 going clockwise. But I really hate going clockwise. Everything is so much nicer going counterclockwise. So the best thing is to flip the middle one with a minus. So my final expression is going to be 1/2 the integral going counterclockwise x squared dy, the outer circle, minus 1/2 the same thing, again, going counterclockwise, the inner circle, x squared dy. So we have to compute both these things. Let's start off with the outer circle. Why is there no dx? Because we chose m equals 0. You see? We have m dx plus n dy, and m is 0. Okay, so for the outer circle, for C1, we will parameterize it as follows. It's the circle of radius 2, so we'll take x equals 2 cosine theta, y is 2 sine theta. So dx we don't even need, dy is 2 cosine theta d theta. And so the integral 1/2 x dy of C1 is just equal to 1/2 the integral from 0 to 2 pi, because we've got to go all the way around the circle. X squared is 4 cosine squared theta, and dy is another 2 cosine theta d theta. So I'm afraid that you're going to have to find 4 times the integral of cosine cubed theta d theta. Yes?
Why there are you not taking the magnitude of the... Don't line integrals, you generally take the magnitude of the velocity function? Is that a different kind of line?
So the question is, why aren't I taking the magnitude of the velocity function? You may recall I showed you 2 types of line integrals. One was just a scalar, say little f ds, and then ds you needed to be v. And then the other one is when you have a vector field and you go f dot dr. And actually you don't need the norm of r there. Everything just works out. You see, this is the same thing as f dot the unit tangent vector ds. Why? Because r, or the velocity vector dr, is v over, well, it's just v dt, which is v over the norm of v times norm of v dt. And this is the unit tangent vector, and this is ds. So it's similar to how when you do f dot n d sigma for a surface, the norms cancel out, or the norm of the gradients cancel out. And technically you don't need them. So this is what's going on here. So everything has been taken care of. And in the differential form, it's even easier. Now that integral is pretty nasty, and I think that we should have done this one. Because when I did it, I did this one, and this integral was much, much easier. But as it turns out, you can see that it's 0 without even doing it. Or I can see that it's 0. I know, I'm so modest. I mean, the fact is that cosine cubed, whatever cosine looks like, there's cosine. Cosine cubed is not very different. You know, it'll be something more like this. But it's still, this bit's going to cancel out with this bit, just like it does for cosine. But you still have to do the integral. So you'll find that this equals 0. All right, so that's one piece. The other piece is a little bit trickier. And there you really wish that you had chosen this one. It's much easier to deal with. But we're going to play along and see what we get. So we need to parameterize the other circle. Does anyone know how to do that? The circle is radius 1, centered at 1, 0. Here's the circle. Isn't that it? Wait, centered at... No, it's this. Okay, so the question is, how do you parameterize this? Well, you just take a standard circle and shift the x-coordinate by 1, right? X equals 1 plus cosine theta. Y equals sine theta. That'll do it. So again, we only need dy, which is cosine theta d theta. And so our integral, the correct way of C2 of, what the hell is it? It's x squared, a half x squared dy is 1/2 the integral from 0 to 2 pi. X squared is 1 plus cosine theta all squared. And dy is cosine theta d theta. So you get 1/2. This is a bit of a mess. So you get 1 plus 2 cosine theta plus cosine squared theta times cosine theta d theta. And if you expand that out, you find you get 3 terms. Cosine theta plus 2 cosine squared theta plus cosine cubed theta d theta. And you actually need this first integral minus the second integral. Well, whatever. I mean, the fact is, when you do the cosine theta thing, you're going to get 0. And the cosine cubed, you're going to get 0 for reasons that I described before. But you still have 1/2 of 2 cosine squared theta. But, of course, you have cosine 2 theta is 2 cosine squared theta minus 1. And so I believe you can write this as 1 plus cosine 2 theta. And this should work out to just be pi. Is that true? I think it's true. So I think that the answer is minus pi. Question?
The whole like shifting over x,
yeah.
Why can't we do that on the problem we did before with the whole law of cosines thing? We had to find the angle.
The question is, why can't you shift it over when we did that cosine law problem a while back? And the answer is that you just can't. No, I mean, that's not a very good answer. The answer is that we weren't looking for a parameterization of the boundary of it. We wanted the whole interior of the thing as well. So it's, I guess you could have done that and used the Jacobian, but then you wouldn't have it in polar coordinates. Polar coordinates have the center at 0. All right, so the final answer, if I haven't made a mistake, is that you have to assemble them into here, and we found that one was 0 and that one was pi, so I think the final actual answer is minus pi over 2. But I could have made a mistake. Sorry, there was a question? Yeah.
Yeah, I understand how you wrote it in parametric form.
Right.
Is there any way that you could just write it as a single polar equation? Like,
To do line integrals directly, you have to do them parametrically. Basically, that's true. Just like in surfaces, you have to do that. You have to do that sort of, grad f over, or do it parametrically. Either they're both parametric forms. So yeah, to do line integrals, always do a parametrization. Okay? Any other questions about this? I want you to try it the other way, by the way, with m equals 0. N equals 0 and m equals xy. I think you'll find the integrals you get are much, much nicer. And see if you get the same answer. If you don't, then I think I made a mistake. But anyway, that's the story. All right, any other questions about that example? Okay, so it's your turn. All right, so we're doing number 8 from January 2006, okay? Okay, here goes. It says, let S be the portion of the paraboloid. Someone actually just asked me about this question during the break, but I didn't do anything on it. So you have this paraboloid, which we're going to draw. And we know that in the xy plane, it's 2, 2, because then since when equals 0, we have x squared plus y squared equals 4. So it's a circle radius 2. So we have this, but we're told that x is greater than or equal to 0, and y is greater than or equal to 0. So that means we only want this portion of it. Okay? So we only want the portion in the first octant. And then it says, let C be the boundary of S oriented counterclockwise when viewed from above. Well, again, we're clearly above this, especially if I do this. There we are. So we want to be going counterclockwise like this. Okay, so here's C, and this sort of looks like a quarter of or an eighth of an orange, but it's not a sphere, so it's just sort of a quarter of a bowl. That is the surface S. Okay, and then finally we have a vector field F, which is equal to y squared, x squared, 0. That's given. They use angle braces and whatever. It's all the same. It's the same business. Okay, part A says state Stokes theorem. So you've got to make sure you can do that. And we want to see, in addition to the standard equation, we want to see some notion that, so here are the ingredients. S is an orientable surface. So I'm not going to write it up because I wrote it yesterday, but we want to see that S is an orientable surface with unit normal n, unit normal vector field, or unit normal field n, with the underline. C is its boundary. So C, capital C is the boundary of S with an orientation that is compatible with n. And then you could put brackets right-hand rule. It's sort of difficult to describe that's what the right-hand rule does. It tells you which way around you've got to go to the boundary given which way you have the normal. Then, if F is any vector field, if F is a vector field, then the equation. Okay, so that's all the ingredients. And the equation we're going to write up in a few seconds. Here it is. Part B. So the equation is f dot dr is the integral of the curl. It's the flux of the curl across the surface. Okay, so that's not Stokes' theorem. That is the equation within Stokes' theorem. Every theorem has an equation in, but that's not all there is to it. So basically, you know, you started with the surface and the C, but you also find there's an N, and then there's an orientation, and you have to explain how it all comes together. All right, so part parameterization for C. And then part C is calculate the line integral using Stokes' theorem. So actually, I'm sort of ahead of myself. This is what I need for parts. Well, I need this in A, that plus explanation, as I described. And the explanation, just by way of summary, you need to say what S is, what N is, what C is, what the direction is, and you need to say something about F. Okay. Anyway, let's calculate this directly by choosing a parameterization. Well, we've got 3 segments of this curve, and we need to deal with them all individually, one at a time. So what I'll do is I'll go over to that picture, and I better label them. I'll call this C1. I'll call this C2, and I'll call this C3. So one at a time. Tell me, what is C1? Well, what is that equation there? Z equals 0. So we have x squared plus y squared equals 4, and z equals 0. So C1 is x squared plus y squared equals 4 for x and y greater than 0, of course. And also z equals 0. So how do we parameterize this in 3 dimensions? Well, the easiest is to use polar coordinates. So I'm going to set x equals 2 cosine theta, y equals 2 sine theta, and z equals 0. It's a curve in space, so it needs a z coordinate even if it's 0. In other words, r is 2 cosine theta, 2 sine theta, 0. dr is therefore minus 2 sine theta, 2 cosine theta, 0 d theta. So I just differentiate. Now we also have to find f. F is just y squared, x squared, 0, which equals y being 2 sine theta, so it's 4 sine squared theta. X squared is 4 cosine squared theta, and that's 0. So we actually need f dot dr is this dot this. So if I'm not mistaken, it's minus 8 sine cubed theta plus 8 cosine cubed theta d theta. And so the integral of this over C1, and that's not a closed loop, by the way. C1 is just that. So the integral of C1 is this integral from just 0 to pi over 2. I stop at pi over 2 because I've only got a quarter of the circle. And it's sort of ugly here. We have to do that integral. So I sort of resisted doing it in the last problem, but I don't see any way of getting out of it. So well, I mean, we don't do power tricks. I'm sure we did in Math 104. I mean, if it's an odd power, you just sort of steal away a cosine theta or a sine theta in the first integral. I'm so lazy, though.
You can just do the problem that's how you do that's not.
Yeah, but I can just do this anyway. No, I can do it very quickly. How would you do that? What's the answer to this? Come on, what is it? It's 0, right? Why is it 0? Look, I'll show you how you never need to do any integrals. Look, here's cosine, here's sine, right? When you cube them, okay, whatever, they've got to be the same thing, going from 0 to pi over 2. It's got to be 0. Look, watch this. Look, integral of sine cubed theta from 0 to pi over 2. Let t equal pi over 2 minus theta. So dt is equal to minus d theta. So this integral, when you're at 0, t is pi over 2. When you're at pi over 2, t is 0. Sine of t, well, cosine of t is sine of theta, because they're complementary. That's what the co means. As in, cosine of pi over 2 minus theta is sine. So this is cosine cubed theta times minus d theta. Don't forget the minus. But you can use the minus to switch this around. So yeah. The integral of sine cubed from 0 to pi over 2 is the same as the integral of cosine cubed, and this is 0. So you don't really have to do either integral. What's so funny? Of course you could do that. I mean, you have to think of it, then you can do it. Well, it only works from 0 to pi over 2, by the way.
It won't work anywhere.
It doesn't seem to work anywhere else. Sure.
Aren't you going backwards on the right-hand side?
What right-hand side?
For the cosine?
You mean over here?
Yeah, you're going from pi over 2 to 0.
Yeah, but I used the minus to flip them around. It's pretty, I mean, it's a pretty snazzy trick, but that's, you know, that's what it is. I never want to integrate cosine cubed if I can avoid it. All right. But, of course, you could just do it directly. Now, we still have to do the other two pieces. So what's, I just erased it, but nevertheless, we can remember C2 was the piece in the YZ plane like this, going like this. So okay, we still have to do this. What is the equation of C2? X equals 0. And we know that this is part of the surface Z equals, what was it? Z minus 4 minus x squared minus y squared. So this, C2, is just Z equals 4 minus y squared. So we just need to parameterize that. And x equals 0. Well, you don't need much of a parameterization for this. There's no polar coordinates or anything like that. If I were you, I would just take that the parameterization is just r is equal to 0, y, 4 minus y squared. After all, x is 0, y is y, and z is 4 minus y squared. But the thing you have to be careful of is that y goes from 2 down to 0. So y from 2 down to 0. So it's a sort of backwards thing. Anyway, dr is equal to 0, 1 minus 2y dy. So our parameterization is in terms of y. What's the vector field? I have, the vector field is y squared, x squared, 0, which is actually, in our case, x is 0 and y is just y. So y squared, 0, 0. And f dot dr, in this case, is equal to this dot this, which is 0, 0, 0. So our line integral from C2 is 0. Okay? That one I didn't need to do anything clever. I can integrate 0 and get 0. All right, and then finally, I'll just cover that up for 1 second. The other curve, C3, that equation now is z equals 4 minus x squared, and this time y equals 0. So I'm going to use the parameterization r equals, okay, so I guess in this integral that I've obscured temporarily, y goes from 2 to 0, if you're going to be really precise about it. But anyway, that doesn't matter. It's still 0. That will be re-exposed in a few seconds. R is x, y is 0, and z is 4 minus x squared. So dr is 1, 0, minus 2x dx. This time f, the vector field, is y squared, x squared, 0. But magically again, this is y squared, but y is 0. So this is 0, x squared, 0. And sure enough, f dot dr is 0, as it happens. So that means the C3 integral is also 0. All three integrals are 0. F dot dr is the integral x goes from 0 to 2 of 0 dx. So the conclusion is that the whole integral is 0. And to solve the problem, you have to do all that. So we finished showing that the integral of f dot dr equals 0 plus 0 plus 0 equals 0. Now, we still have to do the next part, but this shouldn't take too long, hopefully. It says just compute this directly using Stokes' theorem. So again, by Stokes' theorem, f dot dr is equal to what? Well, it's the double integral across the surface of the curl of this vector field dot n d sigma. So we better work out the curl. Curl of f is I, j, k, d dx, d dy, d dz, y squared, x squared, 0. So this is equal to what? Well, those derivatives are nothing. This derivative is 2x minus 2y, which is, no, the j derivative, sorry, x of 0, the j derivative is nothing. The k derivative is something. It's 2x minus 2y. All right, but what's n? Well, to work out n, we've got to go back to our equation for the surface. And I think the surface was z equals x squared. No, it's 4 minus x squared minus y squared. In other words, x squared plus y squared plus z equals 4. Call this f. And so the normal, in some direction or other, is plus or minus grad f over the norm of it, length of it. So the gradient of f we better compute. It's 2x, comma 2y, comma 1. So now what do we get? It's plus or minus 2x, 2y, 1 over square root, oh, here it is again, 4x squared plus 4y squared plus 1. And as it happens, we probably want the plus because we want the normal going up. All right, how about d sigma? D sigma is the length of grad f divided by the k component. Well, the k component is 1. So this vector, 4x squared plus 4y squared, it's not a vector, over 1 dx dy. And so when we work out our integral, curl of f dot n d sigma is equal to the integral over the shadow, which we'll look at in a second, of the dot product of f, of the curl of f, which is 0, 0, 2x minus 2y, dotted with n, which is 2x, 2y, 1 over square root 4x squared plus 4y squared plus 1. So I'm just clarifying, I'm going to take the plus. use plus. The reason being I want the outward normal. And if you look at that picture over here, actually, why do I know I want the outward normal? I have to use the right-hand rule. Bang, out, out, always out with my right hand. So the normal we want points upwards, or the z components are always upwards. So I want the plus one here. And then I multiply by this d sigma business. And as usual, they cancel out. And so I have to integrate over this region. Just the dot product is 2x minus 2y. So I get 2x minus 2y dx dy. Now what is the region? The region is the shadow of the surface. So the region R looks like this. It's just a quarter of a circle. And the circle has radius 2. Okay, so that's the integral that you have to do. Question?
Does the length of rad
Write it out. In fact, in an earlier problem, I didn't write it out because I knew it was going to cancel. So, yeah, it will cancel. Yeah, foresight indeed. So, anyway, this integral I'm going to do in polar coordinates. So, it's the integral. Theta goes from 0 to pi over 2, and r goes from 0 to 2. Notice that theta only goes to pi over 2 because we only want a quarter of the circle. 2x is 2 sine theta. No, 2r cosine theta minus 2r sine theta dr d theta. Okay, we hope that's 0. Oh, I missed the r. You're right, r dr d theta. But as it turns out, the r doesn't matter because notice that I could take a factor of this. I could split this integral up, in fact. I'm going to take out a factor of 2r squared, and notice that this has nothing to do with theta, and this has nothing to do with r, of course. So this integral will bust up, believe it or not, or you can do it in gory detail. But I can already tell you that it's going to come out to cosine theta minus sine theta d theta times the integral from 0 to 2 of 2r squared dr. And again, this has got to be 0 by my same trick. Or you just do both integrals and you find, I mean, you do the integral and you find out that it's 0. So this is 0. And so it doesn't matter what it is, this works out to be 0. Of course, I used a few tricks along the way for these cosine and sine symmetries. But it's interesting how the symmetry that we had, okay, so just to look at it, this wasn't very interesting because the dot product's 0. This wasn't very interesting. So the real action was down here. And the sine cubed and cosine cubed gave us a symmetry when we integrated. And you see a similar symmetry here, although you don't have the cube power, as it turns out. So you do compute it both ways and you get 0. Again, a pretty messy question. 3 regular integrals as well as one surface integral. So there you go. All right. So any questions about that example before we move on? Okay. So I don't think there's anyone left in the queue because he left already. So you have a question. A general question, yes. That will save my hand the writing for a few seconds. If the Hessian, so this is pre-midterm stuff. You have some function of 2 variables. You want to classify the max and min of those functions and the saddle points and the critical points in general. And if the Hessian's positive, then it's a max or a min. If it's negative, it's a saddle point. What if it's 0? Well, I don't have any really good techniques. What you have to do is look at the values of the function close to it and see if you can determine whether it's probably, most of the time, unless you're really unlucky, it's going to be a saddle point. And then you can find points near it which are positive. So one thing you could do is investigate the lines going through. So if it's at 0, 0, then you investigate, say, x comma mx or something like that, and see whether it's always positive along those lines. And if it is, okay, so let me be more precise. It's a general question, but suppose you knew that the Hessian was 0 at the origin, and you want to determine whether the function is, whether it's a max min or a saddle or neither, right? So I guess we're not really distinguishing any other possibilities, so it's probably got to be one of those three. So here goes. Suppose f of 0, 0 is, say, 3. So what I would do is I would say plug in f of x comma mx. Okay? And then you say, okay, well, that is the line of slope m going to the origin. And this is now one variable function, call it g of x, depending on m. And then you can just analyze that function in the regular way, and then maybe 0 is a minimum for that, for one m, and then you have to do it for every different m and see what happens. So if there's any m for which it's a minimum and another m for which it's a maximum, it's a saddle. So that's the best I can offer. It's a messy business. You really don't want that Hessian being 0 if you can avoid it. Any questions about that question or anything I said in response to it? No. All right, so who is next in the queue? 2003, May? Yes. 8 is let f be the vector field given in 3 space given by blah, and then there's a triangle?
Yeah, I think there's
yeah.
tricks that you can do with.
Well, I did that problem yesterday. Were you here?
Yeah.
I think you were. Yeah, this is the one with the triangle. Remember, the triangle doesn't go around the z-axis, so that the integral was 0. I didn't say where the problem came from, but I did that problem yesterday. And by the way, the video from yesterday may already be up. They said by tonight it would be up. But this video should be up tomorrow. But hey, you're either here, in which case you may not need to see it, or you're already watching it, in which case you know it's already up. All right. So any other questions that I haven't already done? Okay. So this is one that I did recently, or didn't I just do this? That was the first one I did.
Yeah, the one.
So you said you didn't understand the solution?
When it says compute div f, how div f equals.
Oh no, this is different. Oh wait, I did do this. I did this yesterday, right? So so this is January 2006. Question 9. And when I did it, I didn't bother computing div f, but I said it was just 0. Did you want me to check that?
Yeah, why is it 0?
Oh, you have to compute it. So, okay, I'm being asked to explain myself for yesterday, where I was indeed quite sloppy for part A. It was just part A that you were asking about? Okay, so my solution was really lame for part A. I just said, you do it. But since you've asked, and this is the Q&A session, I will do it. Okay, and maybe I got it wrong. Hopefully not. So you're given f of xy is 2x over x squared plus y squared, comma 2y of x squared over x squared plus y squared. And you're asked to compute the divergence in part A. So what is... Well, to do the x coordinate, you have to differentiate this with respect to x. Okay, so let's do it. We need the quotient rule. So you're going to do v du dx is 2 minus u dv dx, which is 2x. It's all that over the denominator squared. And I'm not going to do the other one yet. I'll do the y coordinate in a second. So I'm just going to leave a hole here. This is 2x squared minus 4x squared and 2y squared. So you get 2y squared minus 2x squared. No, this is not a vector. I'm sorry. It's this plus d dy of that. So you get 2y squared minus 2x squared over x squared plus y squared all squared. Plus the same thing for doing y. Now, in the interest of saving time, I claim you can just write down the y derivative directly. After all, to get from this to this, you just switch x and y. So when you take the derivative, clearly this derivative is going to be exactly the same but with x and y switched. So you'll get 2x squared minus 2y squared. If you don't believe me, just do the derivative with respect to y. So you get this plus this, which equals 0. So I just gave the answer yesterday as 0 and said you do it using the quotient rule. But it's not obvious. I mean, you actually have to do the computation. But when you do it, you get 0. Okay? I should give this back to you. All right. Have we got anything else? Yes?
It's more like a general thought.
A general thought. Has it really come down to this? Okay, is it philosophical or?
Well, I mean, it's related to what we're doing, I guess. But like, we've done like so much stuff here the past few days that but I haven't seen in class or in the textbook or like any of the homework questions. Is the expectation like really just this much like on you and what you teach us here? Because I feel like, I don't know, if we had done more.
So what you're saying is that we've left it quite late, but in the nick of time. Okay, well, here's the thing. Those final exams have been sitting there all semester, and they were sitting there in December when you already even knew the material in class. And so there is sometimes a disconnect between there's definitely a disconnect between the homework and the quizzes, and then the quizzes and the finals tend to be more of the same level, right? But the onus is on you as an adult and a college student to make sure you know how to do all those past problems. Now, part of the program is predicated that I will be here, the reviewer. All these courses have reviews, and I will be going over problems like this. But the onus is on you to go over problems. So, I still say that I'm prepared to stay here another hour or two and answer the problems. But you see, you have to have them for me to answer. So I'm assuming you've tried them, and that you either understood them, looked at the solutions and understood it, or didn't try it. But there's a question.
Do you know what the past averages have been around?
No, I don't, and they're all curved as well.
But I mean, do you expect people will finish all the problems?
I think that 3 hours should be sufficient for most of the people to finish the exam. But finish doesn't mean they get it all right. I never would leave an exam early unless I was 100% confident that I got it all right, which is basically never. But people leave early. I've seen it. They leave early, okay? Maybe they got 100. Maybe they don't care. Maybe they need that extra hour for something else. But so do you have a math problem? Yeah. You do? Okay. And you also had your hand up. Do you have a math problem, or do you have a general?
No, I was just going to ask about partial credit.
Yeah, I don't know anything about it, but I presume it exists. I'm coming back to the math problem because I want to. Okay, partial credit. Look, it exists. Okay, it does happen from time to time. The problem's out of 20. It's not 0 or 20. I would say that you should always write enough down to indicate that you know what you're talking about, even if you don't. So you try to. The only exception is that if they say, how would you do this problem, blah, and it is not acceptable to say, well, you'd either use Stokes' theorem, Green's theorem, divergence theorem, Lagrange multiplier, and everything, right? I mean, that's not acceptable, okay? But please, I tell you one, okay, since we're doing general techniques and the video is going to run anyway, and I'll come back to your math problem off camera, here is a general sort of set of things that I would do, a general sort of set of policies to follow. So first of all, do not cross out your work very much. If you must cross it out, just put a little box around it and a very light hashing through it. I cannot tell you the number of times that I have seen buried under fierce smudges the correct answer. And sometimes the graders will even find it. But sometimes you will realize that what you did was correct. And it helps if you can see it. Okay, so you can just do that. Second, please write sentences as much as possible. Write sentences. Explain what you're doing. That's the way to get partial credit if you don't get the problem exactly correct. Even if you do get the problem correct, sometimes you need to say things, justifications, to get all the credit. So if you use Stokes' theorem, by Stokes' theorem. Okay, I guess you can write Stokes, and that's probably enough. But you should try to write some sentences. Finally, if you have a chance between now and Saturday, I strongly advise that you take one of these finals, the past finals under exam conditions, preferably one that you haven't looked at. So you should try to spend 3 hours. And I said it before, I'll say it again. Take 3 hours where you can just sit there and not be disturbed by anything. No cell phones, no IMing, email, you know, no iPods, whatever is going to be in the exam, you should try to simulate that. Do it. Write it out. Don't look at the book. And then look at the solutions or ask the professor or email me and say, look, can you just check my answers to this? And, you know, I'd be happy to do that even in the next couple of days. So if you do that, you'll be much, much better placed for that. Okay, so those are my general sort of thoughts about how to deal with this upcoming exam. And I think you should have time, hopefully, to find that 3 hours. But I don't know how many other finals you have in the next day or so. So maybe that's, I do appreciate there's other things going on in Math 201. So, look, that said, I think I'll just stop the video here, but not the session. So, thanks to all for watching.